Hi, I'm Tom. I'm a master's student at the University of Hull, and I'm here to talk to you about exploring deadly volcanic currents or pyroclastic density currents and my research into them. So we'll do a brief introduction to what pyroclastic density currents are before we get into this. So as you can see in this video of Mount Aso in Japan, where the eruption bursts out and then the ash cloud falls down and flows rapidly along the ground towards the camera. The distance between this camera and the actual volcano is 3 kilometers, so that's about 40 minutes walk. So before we get into a bit more detail about what these flows actually are, we need to look into why we studied them and why I'm doing this research. So 600 million people live in areas affected by volcanoes, so we really need to understand the hazards they face. And of all the volcanic hazards, pyroclastic density currents are responsible for 33% of volcanic fatalities. So by understanding these flows better, we can protect people and save lives in the future. So you can see in the table here just some examples of different volcanic hazards that are posed during eruptions, especially ones that are fatal. So then more into what pyroclastic density currents are. Well, these are hot flows of different gases, volcanic ash, and material like rocks and lava. So you can see in this photo, it's a Mount Pinatubo eruption in 1991, and you get these large clouds of ash billowing above this main flow along the ground. So we'll watch another video to give you an example of the scale of PDCs. So this here is an eruption in Indonesia called Sinabung, and this is from 2015. And you can see here that the flow is going down the hillside very rapidly and then along the valleys in the flat with these large billowing clouds above the main flow. And these flows are going to destroy trees and fields, and they're going to surge along very rapidly before this cloud picks up more air and then rises up, forming these very high columns you can see at the end here. And eventually this will fall back down, leaving a layer of ash along the ground. So these kind of videos are very good to show the scale. So actually, as an example, the highest point there was 2.6 kilometers high. So if you think that's just a little bit shorter than the distance from the volcano in the camera in the last video, so you can kind of see these very high, they're able to rise very high into the atmosphere. So now we've seen what these flows actually are, we can look at what they deposit, and because of this, how we can study them. So the most famous example of a PDC deposit is in Pompeii, where the flow from Mount Vesuvius went through the town and covered buildings entirely in these ash deposits. As you can see in the photo here, it forms these very solid rock layers with more fine ash above. So then what actually is included in these deposits, it's important to understand. So we have pumice, which is on the left here. And this comes from cooling magma, where you have bubbles of gas inside, and this actually traps and forms these air bubbles within. And then you also have volcanic ash, which is on the right here, and this is actually not like ash in a fire, but it's very small fragments of rock, so very smaller than 1 millimeter, so they're very sharp and dangerous. So we can see some examples of what PDCs deposit, and therefore what we actually study as volcanologists. So the first photo here on the bottom is from Mount St. Helens, which erupted in 1980. And this little dot at the bottom where my mouse is a person. So you can see these deposits are very large, they're so much bigger than a person. So they're really important to understand because of how much they cover. And then you can see how variable the actual flows are from these other two photos. So this one on the left here is from southern Spain. And there's a lot of different blocks varying from the size of someone's head right down to the fine ash of a few millimeters. And the same in this photo of Tenerife, where this black material is different pumice. So you can really see there's a lot of variation going on in these flows. And on a more small scale, again, you have a lot of variation with some photos here from Spain, where you have sort of rocks from the inside of the volcano being pulled out, in amongst lots of fine ash and these crystals. And similarly, this is an example from Snowdonia in North Wales, where you get very large blocks that can be 30 centimeters in size and in some cases even bigger actually. So again, not only is there a difference in materials, but we're seeing a lot of variation in size. And this is quite important to understand because it affects how we judge the hazards, from the size of the particles being maybe more destructive as it hits buildings and cars and things. So then we'll moving on to how we understand them, because at the moment we don't really understand how pyroclastic density currents flow well. So my work researches how fast and how far they flow depending on the size of the material in the flow. And then we can compare what deposits this leaves, what we see in nature. So if we look at this video here of a recent experiment I've carried out, I've been releasing this material from the top and it flows down the flume and forms this big sand deposit. So this material here is actually made up of fine beads of glass, and we're releasing them down the tank and filming so we can judge the distance, measure the distance, and calculate speed. And you see we use videos like this to really make more useful observations. So if you see here, we record actual flow in a high-speed camera, so we create this very detailed video. So I can make measurements of distances and the time, and we can actually work out how fast this flow has travelled. And also by watching the video, we can observe different behaviours within the flow and see what behaviours are actually happening between these particles. And by understanding these, we can begin to apply them to real life pyroclastic density currents and sort of expand our understanding. So why do we need to understand them? Well, if we understand how pyroclastic density currents flow, we can begin to expand our knowledge and predictions of where they're going to travel. So we do this to create hazard maps. So this bottom one's of Merapi in Indonesia. So the more we understand, we can change our understanding of where they're going to flow. So maybe at first we think it's only going to really flow here, and then as our understanding changes, we realise there's more risk in the south to these towns. So by understanding these, we can create which cities are at high risk and evacuate people much sooner, and therefore it makes everything safer for people. So that's my research, and we need to think, so hopefully that's interesting for you, and you can begin to think about what you want to do in the future and how a degree in geology can help you sort of go into different careers or skills of anything you want to do. Because a degree in geology teaches a wide range of skills, from leadership to project management, time management, communication in sharing presentations like this and writing reports, as well as problem solving and different research skills. As you can see, we have a problem that we don't understand about pyroclastic density currents. So then we come up with ideas of how to research this. But also geology can lead to a range of careers. So you can be a researcher or a lecturer doing research into a particular aspect of geology like I am. Or you can be a geotechnical engineer, a resource geologist, or do environmental monitoring, where you kind of investigate how the geology impacts the lived environment, of whether it's safe to build houses in a certain area, or there's maybe resources that we can use, not just oil and gas, but also what we need for renewables, such as geothermal energy. And this leads into more sustainable roles where we have geology graduates taking part in jobs to do with the renewable energy development or disaster management plans and water resources. And especially you'll develop skills around a wide range, so you can begin to investigate climate science roles. So if any of them interest you, then a degree in geology could be something you want to look into. So thank you for watching my talk. I hope it's helpful and interesting for you.